Alrighty, guys, welcome back for part 2 of our hormones in hypothalamus, or I cannot talk, hypothalamic control discussion exercise 3. So this one's going to be shorter than the last one. Let's hop right into it because I bet you'll be tired. I am pretty late at night. Okay, so going to my discussion. Let's get this loaded and going. Now we're going to hop on into question number 4 because that's where we left off. So this is a pretty simple question. It's looking at our hypothalamic control pathway, which we already looked at in number 1, and specifically looking at T4 and T3, our thyroid hormones. So what functions as the first integrative center? That's always going to be the hypothalamus. The hypothalamus will always be that first integrating center of our hypothalamic control pathway. So that is going to be the hypothalamus. Our final integrating center is going to be the thyroid. This is specific to which pathway we are talking about. So if we were talking about the sex hormone pathways, it could be the gonads, it could be the adrenal cortex. It's specific to which pathway we are discussing. Whenever we look at the first efferent and final efferent, one thing that y'all can kind of use as a trick to remember those things. So anytime I see efferent, I think exit, efferent, exit. And then afferent is going to be arrive or approach, whichever one you would prefer. So whenever we're talking about that first efferent function, what we're going to see is that's going to be TRH, thyroid releasing hormone. It's going to be that first hormone that's going to exit the hypothalamus and stimulate the release of thyroid stimulating hormone, which will stimulate the release of our final efferent hormone, which is thyroid hormone or T4. All right, awesome. So the next one is asking about our thyroid hormones being synthesized while attached to a large protein, which we are looking at thyroglobin. So T3 and T4, if you remember back to lecture, are steroid hormones. They're a single amino acid, and that means they are hydrophobic and lipophilic. So what that means is they cannot be like pre-packaged or stored on their own. Because they're hydrophobic, they will just diffuse out of the cell with that concentration gradient. So we will use thyroglobin, this protein, to kind of block them or trap them inside of the cell. So what it says is just before releasing those hormones from the thyroid cells, they will be stripped from that protein to become lipophilic. So they can now leave the cell once stripped from that protein. And with that information, we can now look at the following questions. So question A says, by what method of movement do our thyroid hormones leave the thyroid cell? That's just going to be simple diffusion with that concentration gradient. Steroid hormones are in higher concentrations inside the cell, lower concentrations outside. So they'll move with that high to low via simple diffusion. B says, how does thyroid binding globulin function? So this is when we're looking at that thyroid globulin, that large protein that we see right here. So what it's going to do is overall, it's going to trap those thyroid hormones inside of the cell. That's kind of what we discussed earlier. It's going to trap T3 and T4 inside. And again, I can explain that once more. T3 and T4 are steroid hormones, which I guess I will go ahead and just write this down for you in case you missed it in lecture. What we see is that our steroid hormones, let's see, I'll write it right here. Our steroid hormones and our protein hormones have two different functions. I can kind of draw this out. So our protein hormones not protein hormones, but just our proteins are hydrophilic and lipophobic. Our steroid hormones are the exact opposite.
hydrophobic, and lipophilic. So that lipophilic. So what we're going to see is that the T3 and T4, those are steroids. So they are hydrophobic, meaning they are going to want to enter into the cell, or sorry, leave the cell. And that protein is going to trap them in there because it's lipophobic. It is scared of crossing that membrane. So that thyroid binding globulin, the large protein, is going to trap the thyroid hormones inside of the cell. Once we go ahead and clip that off, they're going to be free to leave the cell. The thyroid hormones will be free to leave the cell because they are steroids, hydrophobic, lipophilic. They do not mind leaving. They are not afraid of the membrane. All right, great. So C is asking, give a teleological reason for why T3 and T4 have a nuclear receptor. To answer this, we need to know what teleological means. This is asking for the why, so not just how, but the why. And so what we see is that T3 and T4 have this nuclear membrane, sorry, I cannot talk tonight. T3 and T4 have a nuclear receptor because they can diffuse past the cell membrane. So our answer here is going to be because they can diffuse past the cell membrane. And some reasoning behind this. Those steroid hormones, the receptor is usually on the DNA itself, which will act as a transcription or translation factor. A little review back to genetics or functional biology. Those transcriptions and translation factors will take DNA, convert it into RNA, break it down to a single amino acid, which will string together to make a new protein. So those steroid hormones, the T3 and T4, it's really important to know that they stimulate production of new proteins. And when we do this, they will diffuse past that cell membrane instead of just existing elsewhere. All right, great. And moving on to number 6, which is more likely to be an effect of T3 and T4? Circle the correct answer. So this kind of goes with what we said above. Here our answer is going to be A, stimulate production of sodium potassium ATPase subunits. So our keywords that we see here are going to be that stimulate production. And our sodium potassium, that is a cell membrane protein. So that is exactly what we just talked about, that taking that DNA, converting it into RNA, and stimulating that production of new proteins. Whenever we see our alternate thing, we see upregulate sodium channel activity. This is talking about sending those existing proteins, the sodium channels, to the cell membrane. So they send it to the cell membrane instead of just being on the DNA itself as a receptor. All right, great. And then one more thing, if you're looking at this IP3 and you're a little bit confused about what it is, IP3 is a second messenger. And super important to remember from lecture, second messengers, protein hormones use them, steroid hormones do not. So we would know that B is not our answer because steroid hormones do not use that IP3, that second messenger. All right, awesome. So this is going to kind of be our last one, number 7. So let's hop on into this. So before we begin, we kind of need to know what's going on this chart, what we're looking at. So the x-axis is looking at the concentration of thyroid hormones, of T4. So what that means is when we move from the left to right, we are going to see an increase in thyroid hormone. Our y-axis is looking at thyroid stimulating hormone, TSH. So what that means is as we move up the y-axis, we're going to see an increase in thyroid stimulating hormone. These values that are grouped together right here in the middle are kind of just those normal conditions. These ranges up here and down here are kind of indicating some type of pathological or abnormal condition. So 7A is asking which symbol represents data from a hyperthyroid condition, So what does hyperthyroid mean? That's going to be an increase in production of those thyroid hormones. So hyper, an increased production of those thyroid hormones. What are our thyroid hormones? That is going to be that T4. So we look at our chart and that means we are moving this way. So the symbols that are going to be representing that the most are going to be our circles. Nice. So B is saying, does the data indicate primary hyperthyroidism or secondary hyperthyroidism? So we can go back to that original design we were using, looking at our cascading hormones. We have that TRH, that TSH, and that T4. We know we are having an increase in thyroid hormone, so we can increase that right there. And what we see is that that increase in thyroid hormone will, the hypothalamus will detect that and it'll respond by decreasing the amount of thyroid releasing hormone, which will decrease the amount of stimulating thyroid stimulating hormone. And that is one of our tropic hormones, and we see that that does not match up with our thyroid hormone response. That shows us we are having an abnormal response, aka a primary hypersecretion. So primary hypersecretion. Great. Okay, cool. So number 8 kind of goes just along with number 1, kind of looks at that pathway for that hypothalamus or hypothalamic anterior pituitary pathway. So go ahead and go back and look at number 1 and kind of look at these options and do it on your own. Go ahead and give you the answer now, just so you can check yourself. C. And then lastly, number 9, I know this sounds like a really scary one, and it is kind of scary. So we just wanted to let you know you will not be asked to make up things on your exam. So for this question, I would recommend reviewing permissiveness, synergism, and antagonism. This is what that question is kind of wanting you to think of and dissect. So don't worry about trying to make up something in your own mind. Instead, I would recommend that you review those 3 mechanisms: the permissiveness, synergism, and antagonism. But that is all I have for y'all. I will see y'all maybe in class or next week after your exam. Have a great evening or morning whenever you're watching this. Bye, everyone.